This is question 5 from January 2005 on module 4 paper. First question is standard start to a gravitational question to state Newton's law of gravitation. And what we need to remember there is that there are 3 marks available, so we have to say that every body attracts every other body. So that's 1 mark for that. Attracts every body, attracts every other body with a force which is proportional to the product of the masses. And inversely proportional to the square of their separation. This is another standard type of question to do with satellites. Assume that the planets move in circular orbits about the Sun. Use Newton's law to show that for a planet in an orbit of radius r and period t, t and r are related by this, where a is a constant. Give an expression for a in terms of the mass m of the Sun and the gravitational constant g. State the SI units of a. Alright, well, first of all, we have to say that there's a centripetal force F equal to m or omega squared, and that is equal to gmm over r squared. That m is going to cancel out with that, so we're left with r cubed omega squared is equal to g times m. Alright, well now I've got the r cubed that I'm looking for, so I need to get t into this somehow. So the next thing that we need to say is that omega equals 2 pi over t, or t equals 2 pi over omega, whichever way you want to give that. Therefore r cubed times 2 pi over t all squared equals gm. So I now have r cubed times 4 pi squared over t squared equal to gm, which if I rearrange that gives me t squared is equal to 4 pi squared over gm times r cubed. 4 is a constant, pi is a constant, g is a constant, and m, the mass of the Earth, is a constant, or the mass of the planet. So we've got t squared equals a times r cubed, where a is going to be 4 pi squared over g times m. The SI units then of a, well, in order to work out the SI units of a, we're going to have to do a little bit of work there, because it's 4 pi squared on the top line and then it's gm on the bottom. Now g has units, right? And if we look at our formula sheet, you'll find the units for that. So the gravitational constant, okay, if we look on our formula sheet, what we'll see is it's Newton meter squared kilograms to minus 2. So we have a has units, okay, 4 pi squared over gm. Therefore its units are going to be, on the bottom line we have Newton's meters squared kilogram to the minus 2, and then we're multiplying by kilograms. So the SI units of that will be kilogram to minus 1 on the bottom becomes kilograms on the top line, and then we have meters to the minus 2, and then we have newtons to minus 1. So the SI units for that will be kilograms, meters to minus 2, and to minus 1. Right. we're going to use what we've just done in a calculation. In March 2004, astronomers announced they discovered what may or may not be a very remote planet to which the name Zenda has been given. They estimate the distance of Zenda from the Sun is 86 times the distance of Earth from the Sun. Assuming that Zenda is a planet in a circular orbit about the Sun, use equation 5.1 to estimate its period. Right, and this is in terms of Earth years. So what we're saying now is that t squared is equal to a times r cubed. So if we consider that equation in terms of the information that we've got in the question above, what we're saying is that for the Earth, t for the Earth squared is equal to a times the radius of the Earth's orbit around the Sun cubed. And for Zenda, we can say t for Zenda is equal to a times the radius of Zenda cubed. So if we consider this, I can rearrange that and say a is equal to ts squared over rs cubed, which is also equal to te squared over the radius of the Earth cubed. And we're told that, if we look in the question again, that Zenda, as the distance of the Sun, is 86 times the distance of the Earth. So what we've got now is that ts squared over 86 times the radius of the Earth cubed is equal to the period of the Earth squared over the radius of the Earth cubed. So we now have the radius of the Earth cubed is going to cancel across, so that the period of Zenda squared is equal to the period of revolution or orbit of the Earth about the Sun times 86 cubed. Now the radius, that cube and that re cubed and re cubed went out there, so I'm left with 86 cubed. So that means that the period of Zenda is equal to the square root of 86 cubed times the period of the Earth. So the period of the Earth is 1 year, so it's that times that, so it's equal to the square root of 86 cubed, and when we calculate that, that turns out to be 798 Earth years. Okay, so just to go through that again, we're using the t squared equals a times r cubed. So we do it for the Earth, we do it for Zenda, and then I'm equating both of those, working out what a is for both of them. So it's ts squared over rs cubed, te squared over re cubed, and we know for Zenda that it's 86 times the radius of the Earth cubed. The radius of the Earth then goes out, and we're left with a calculation which is the square root of 86 cubed times the period of orbit for the Earth. And that is the end of that question.